Hi, I'm Jayanth Chirumalla. In this video, I'll be presenting about the topic CNT-based EMBG resonator for CO2 gas detection. This is as part of the course ELG 7132 Topics in Electronics 1, Nanoelectronics. Here are the contents of this presentation. Introduction, design and fabrication of the CNT-based EMBG resonator, experimental setup and characterization of the resonator, limitations and future work, summary, and references in the end. Let's start with the introduction. The main aim of this project is to detect the presence of carbon dioxide gas using a new device that has been proposed which uses electromagnetic bandgap resonator, which in microwave domain is analogous to the photonic bandgap structure at optical wavelengths. And it basically is an artificial periodic structure that prohibits the propagation of electromagnetic waves in a certain frequency band. The proposed EMBG resonator was designed by introducing in the central region of a coplanar waveguide a couple lines of section covered with a thin single-wall carbon nanotube layer. Now, S parameter values have been recorded in microwave frequency ranges for the setup with and without carbon dioxide gas, and plots are drawn between transmission magnitude, phase, and sensitivity over frequency in GHz for varied values of carbon dioxide concentration to demonstrate the results. The basic idea of this research was from few of the previous works where EMBG resonators have been used along with multi-wall carbon nanotubes to detect methane gas and a new sensor to detect and monitor the carbon dioxide gas in the human respiratory system. Moving on to the design and fabrication part of the resonator, EMBG carbon dioxide gas sensor of size 4650 by 3950 micrometer square with coplanar waveguide is used, along with 4 micrometers single wall CNT layer is used, which is able to detect the presence of carbon dioxide molecules by means of a shift in the resonance frequency. As mentioned, the smaller size of the device component makes it compact and the measurement technique used reproducible and repeatable, and the technique is consistent across different uh, value ranges of concentration of carbon dioxide gas. Coming to the structure of the resonator, it's formed by 6 periods with a defect region of 50 micrometer between them, which we can see in the picture, which is in the upcoming slide. Uh, Here, W equals to 330 micrometers is the digit width, and S equals to 330 micrometer is the distance between two consecutive digits. So this basically is the structure of EMBG resonator that we're talking about, and this is the digit width, which was denoted by W in the previous slide, and this is S, which is the distance between two consecutive digits, and this particular region is the defect region of the resonator. EMBG devices, based on their resonance structures and design, exhibit specific impedances. The nature of good coupling between CNTs and the coupled lines of EMBG resonators, similar to one which we are talking about, was demonstrated for DNA hybridization in one of the related works. The resonance structure was simulated by means of 3D electromagnetic simulator, and the resonance frequency along with moderate losses was found to be around 21 GHz. And the exact frequency response of 22.16 GHz can be seen in the next slide. So here is the frequency response of EMBG resonator in the band of 20 to 25 GHz, and here we can see a peak of 22.16 GHz at minus 25.2 dB. Moving on to the fabrication part of the device, the EMBG device was fabricated on silicon dioxide high reaction silicon wafer, and the steps performed in the fabrication process were listed below. Cleaning of silicon wafer, thermal growth of 500 nanometer thick silicon dioxide layer, metal deposition via sputtering technique with thickness of 30 nanometer by 300 nanometer respectively. The steps followed for optical lithography are listed below. Treatment on hot plate of 100 degrees centigrade for 10 minutes, and photoresist deposition by spinning with thickness of 1.5 micrometer. UV exposure, developing in the end. Metal deposition etching through photoresist mask, and in the end, cleaning in isopropyl alcohol and DI water in an ultrasonic bath for 1 minute. The resonator was loaded with single-wall carbon nanotubes of 90% purity, which were dispersed in chloroform to a concentration of 2 mg per ml. Then the dispersion was sonicated for 5 minutes. An aluminum scotch mask of 50 micrometer thickness was patterned with small holes, was applied over microstructures for drop casting. The wet film then was allowed to dry for 30 minutes at room temperature, and then the scotch mask was removed. The SWCNT layer was then fixed on the center of EMBG resonator and allowed to dry at room temperature. This is the picture of EMBG resonator before fixing the SWCNT layer, and this one after fixing a thin layer of SWCNT layer in the center of the EMBG resonator. And here we can see some detailing of the carbon nanotubes with their diameter dimensions marked. Moving on to the experimental setup and radio frequency categorization of the CNT-based EMBG resonator. The results presented in this paper were obtained using an experimental setup composed by a metallic chamber with a volume of 3.61 diameter cube, posed continuously with carbon dioxide gas until an atmospheric pressure of 1/2/3/4 over the device was achieved. Here we can see the complete picture of the experiment setup, and here the device under the text fixture. The concentration of carbon dioxide molecules in terms of number of moles can be calculated by applying the well-known van der Waals equation, wherein the equation P is the pressure of the gas, N is the number of moles, V is the occupied volume, R is the universal gas constant, and T is the temperature, and A and B are the constants. By applying all these values directly in the equation, we can calculate the values of concentration and molarity. Now, from the plot drawn between concentration, molarity against pressure, it's clear that the molarity value increases as in increase in the concentration values. Now we can see that there is a maximum value of molarity of 0.165 at a concentration of 72% of CO2 gas. The resonance frequency of the device was found to be around 22.16 GHz. The presence of SWCNTs shifts the resonance frequency at 23.6 GHz and decreases the quality factor of the device. Now S parameter values of the device have been recorded with no gas and with CO2 gas and increasing its concentration. Now from the magnitude plot, we can see that there is a frequency shift of 135 MHz from 23.726 GHz with no gas to 23.591 GHz with CO2 gas of concentration 72% at resonance frequency. It's also the same with the phase plot. Now there is a phase shift of 26.33 degrees with 34.72 degrees with no gas and 61.05 degrees with CO2 gas of 0.72% concentration at resonance frequency. Sensitivity of the device was calculated using the following equation, where mod Z in Z is the input impedance of the device with gas and mod Z in O is the input impedance of the device without gas. Now taking the results mentioned in the previous slide into account, sensitivity value has been calculated, which found out to be 29.72% for CO2 gas concentration of 0.72%. Moving on to the limitations and future scope, due to the presence of low purity SWCNTs, there is a significant difference as far as the resonance frequency of the device is concerned, but it made the device less control in drop deposition and the quality of the resonator has been decreased. But nevertheless, there is a lot of scope for more experiments and further investigations can be performed to enhance the potential offered by the EMBG resonator along with single-wall CNTs. Moving on to the summary and conclusions, a new type of gas sensor was proposed which is based on EMBG resonator with couple line structure in the central area, which is covered with SWCNT layer of low purity, which is able to detect carbon dioxide gas by changes in the impedance values at the resonance frequencies. A phase shift of 26.33 degrees with resonance frequency shift of 135 MHz has been observed for CO2 gas of 0.72% concentration. and a very high value of 29.72% sensitivity has been observed even with low purity SWCNTs used. And as mentioned earlier, there is a lot of scope for future experiments to improve the performance of the sensors and to characterize them over a larger carbon dioxide concentration range. These are the references, and thanks for watching. Thank you.